CID 1255.
Good afternoon, Professor.
Yeah, good afternoon.
Simple question. Actually, what is the application of inclined manometer, sir?
It is for measurement of pressure, and as I discussed, it gives you better accuracy, because by making it inclined, you are increasing the reading of the manometer, that is the distance by which the fluid rises in that column. Now, suppose you have measuring it by a simple scale, the least count will be about 1 millimeter. Now, your measurement cannot be more accurate than that. So, there is always an error or uncertainty of about 1 millimeter. Now, if your measurement is say 1 centimeter, then your error is 1 by 10, which is 10%. If your measurement is say 1 meter or say 50 centimeters, then it is 1 by 500. So, there is a big difference. So, usually when you measure anything, you want the reading to be large, so that the relative error is small. So, that is why inclined manometers are preferred in some application.
Thank you, sir. Thank you, sir.
You are welcome. One zero one four.
Hello, sir. Good afternoon, sir.
Good afternoon.
Hello.
Yeah, good afternoon.
Sir, I have taken a glass of water. I have taken a straw, sir. So when I am immersing this tube inside the glass of the water, and if I close this pipe and if I release this, I am getting the water, sir. And if I close this pipe and if I immerse this and if I remove this, I am not getting any water. May I know what is the basic reason behind this?
I didn't follow. Can you repeat the question? You are taking a
Initially, I have taken one in the closed pipe, sir. One in the closed pipe, and I immerse this
okay.
inside the water,
Uh-huh.
and I release this, sir.
Uh.
And now I am not getting any water, sir. But when I immerse this with open tube, now I close this one. Again, now I lift this. When I am opening this, I am getting the water, sir.
So, you want to know why the water goes up? It is because of capillary action.
Is it due to capillary or change of pressure or body forces?
Body forces are always there, but you also have a pressure difference. So, it is a balance between all of those.
So, both capillary and pressure difference exist.
What you are looking at is a transient phenomenon, the water rising up the tube. Now,
yes, sir. What
suppose
what is the inside the tube?
Suppose you just insert the tube and let the water rise and reach a steady height and stop. Okay.
Yes, sir. Yes, yes.
So, one steady equilibrium has been reached. Okay. And then if you close the top end, you are keeping the pressure the same and you are lifting it up, the water is there.
Yes, sir. So, pressure at the top and bottom are same in that way.
Now, bottom pressure depends on how much you have inserted the bottom means pressure at the bottom of your tube will depend on where you what is the position of the tube in the immersed liquid column.
Okay. Okay.
1107.
Hello.
Yeah.
Hello.
Yeah, we can hear you.
Good afternoon, sir.
Good afternoon.
Sir, you have written del P upon del Z equal to dF upon del dz. how is it possible force can be equated to pressure?
I didn't get you. What I was?
Hello,
Yeah.
hello, hello,
RCID
hello.
1107, your video is not coming.
Your
RCID,
video is not coming.
Your video is not coming. RCID 1107, your video is not coming. Please switch on your camera.
You have written del P upon del Z equal to del F upon del Z, and that is equal to minus rho G. So how this pressure can be equated to force?
What is? There is not a force. It is a function.
Okay.
RCID, we are not getting your video.
Thank you. আমি কোশ্চেনটাই বুঝতে পারছি।
Hello.
1235. 1235. RCID 1235. Yeah.
One,
Yeah.
2, 3.
1235.
Go ahead.
I have a question.
Yeah.
Sir, I'm speaking. Are you able to hear?
Yes,
Yeah.
yes, yes.
Sir, I have an idea. It is actually possible, but it violates the first law of that word. We have multiple number of capillary tubes, and using capillary tubes, we pump water to a certain height, and we make the water to run through a turbine. So this way, we can generate power without any input. Is possible?
Can you repeat the question? I didn't get it.
Audio is already clear. Using capillary tube, we pump water.
Audio is not clear.
Using capillary tube, we pump water to a certain height, and we allow the water to produce work through a turbine. So this way, we can generate work without any input. So is this idea possible?
No, that cannot be possible.
Why, sir?
How will you get the water up to a pump?
Sir, we have to use so many number of capillary tubes. So that way, we can pump water to a certain height.
But how will you store the water? You have to store the water somewhere before you can let it go through the turbine.
Yes, sir. We put a tank at some height, and we store the water over there, and we let that tank
No, but
water to.
have you done an experiment and shown that the capillary action can raise it up to the tank?
For example, in case of a trees, water is being sucked by using the surface tension.
Continuously.
ট্রি তে বলছো ট্রি গাছে যে
Yes, continuously, sir. Yes, sir.
গাছে যে জল ওঠে বলছে গাছে জল ওঠে তো গরম করে জল তোলা যায় উপরে তো খুব সামান্য জল উঠবে তো যদি কিছুই হবে না
ওইদিকে একটা evaporative flux হতে হবে। দিন না একটা
আপনারা বলে দিন
আপনি
Now, what you want is a continuous generation of power. So, how will you get it? See, water, if you put a capillary tube, will rise up to a certain height inside the tube. You want it to go all the way up out of the tube and into a tank. Is that possible? You have to let the water rise all the way up the capillary tube into a tank, and then from there you can do it. But will it rise all the way up? That is the question.
Ahead of it, sir. Maybe ahead of the around.
next.
Okay, sir. Thank you. Thank you.
ওয়ান ওয়ান ফোর ফোর
1144. I IIT Bombay Remote Center.
Hello.
Yeah.
Afternoon, sir.
Good afternoon.
Hello.
Yeah.
Are you getting me?
Yeah.
Sir, how the kinematic steel and water are same?
Can you speak a little louder?
How the kinematic viscosity of water and steel are nearly same. Yesterday when sir told us.
If you divide the properties, they are the same, come out to be the same. Almost.
No, I didn't get your question. Kinematic viscosity of?
Water and steel, liquid steel,
What's the
molten steel.
kinetic viscosity of liquid water and molten steel
Kinematic
are
viscosity of steel and water are nearly same.
So, well, if you measure it and
Steel and water.
it could be close.
Sir, I repeat the question. How the kinematic viscosity of steel and water are nearly same?
See, it's steel, you are talking about molten steel, right?
Please repeat the fact.
See,
molten steel.
Yes, water and steel.
no, first of all, I don't have the data. You have to look at a handbook and see whether what you are saying is correct or not. But even if it is correct, what is wrong with it? Why shouldn't it be the same? It is not solid steel. You can't define viscosity for a solid. It is a molten steel, right? The values may be close. It may also depend on temperature. Viscosity will depend on temperature.
Sir, yesterday.
For certain temperatures, it may be the same.
Next one, next one.
One more question.
One more question. Give me a. Sir, viscosity is directly inversely proportional to temperature in case of liquid. Okay.
No, why should it be inversely?
Proportional
It is not inversely proportional.
in case of liquid.
From where did you get this fact?
In case of liquid, but
No, it is not true. It decreases, but why should it be inversely proportional?
inversely proportional, but indirectly proportional in case of gas. Why? Explain it.
See, first of all, I don't agree with your statement that it is.
Directly proportional in case of gas.
It is not directly proportional. Directly proportional means if you double it, the temperature, the viscosity will double. What you mean is it will increase, and in one case it will decrease. That does not mean it increases directly, and the increase is in direct proportion. Okay, you have to be precise when you make a statement. See, in the case of gases, it is due to molecular motion. Okay, so with increase in temperature, the molecular activity increases. Exchange of momentum between layers increases. In the case of liquid, it is due to cohesive forces. So, when
It's not directly proportional.
it is not directly proportional. Who has given you this idea it is directly proportional? Directly proportional means mu is equal to A plus Bt. It does not increase like that. Can they ask?
Thank you, sir.
এরকমই কোয়েশ্চেন স্যার ম্যাক্সিমাম
না আজকেই যা পড়ালাম তার উপর তো কোশ্চেন করবে নাকি?
1303
হ্যাঁ এটা আপনি বলে দেবেন
Hello.
Okay, I have a request. Please ask questions related to today's lecture. We will give a top priority to that.
Sir, I have got a question from capillary rise, sir. I have got a question from capillary rise. We have derived the equation for the capillary rise keeping the tube
Okay,
vertical.
no,
Now,
I will
if
give.
we slant, if we keep it in a slant,
No,
how can we account for
Okay,
that?
please listen to me. I did not teach you capillary action, so probably it will be better if you address this question to the teacher who taught you capillary action. Because this time is short, I will give priority to questions related to the lectures which I made today. If you have questions related to today's lecture,
Okay, sir. Okay. Sir, you have derived the equations for. Okay, sir. Sir, you have derived it, integrated so many times, and you have got a constant. Whether it has got any physical meaning, sir, because in the normal textbook we can't find the constants anywhere. Like for the hydrostatic force that you have derived for a slant laminar. So there also a constant is coming. Whether it has
the constant can be
the physical meaning, sir. How can that C stands for what, sir, exactly?
Okay, that C came when you integrated the differential equation.
Mathematically we can understand. Does it have any physical meaning?
See, you can find what is the constant C by applying the bounding condition that the pressure at the free surface is atmospheric pressure. I skipped that part because even without discussing that, I was able to derive the result. So, due to lack of time, I did not bother to find out the C. You can find the C by setting P equal to P atmosphere at the free surface. One 1161.
Hello.
Yeah.
Hello.
Yes, please.
Good evening, sir.
Good evening.
Sir, regarding viscosity, am I audible, sir?
Yes, but do you have any questions first of all related to today's lecture?
Actually, on today's session, I have no questions, sir. From yesterday's topic only,
There are so many centers and we are short of time, so I would have preferred questions related to today's lectures.
Okay, can I ask a small question, sir? That is,
okay, go ahead.
What is the difference that makes fluid viscosity in steam power plant and fluids that used in fluid mechanics, sir?
Can you repeat
Is there any difference?
In what? Difference in what?
So the difference of the viscosity that is used in the fluids in the power plants to that of the fluid in the fluid mechanics that we are using. Will be there any difference between the viscosities?
See, viscosity of a fluid will depend on temperature, pressure, composition, concentration of dissolved solids, etc. So, if it is a fluid, viscosity, definition of viscosity is the same. The value will depend on the conditions. So, if you have pure water, it will depend only on temperature.
Yes, sir. So the derivations that we are doing today, sir, can we able to teach the same kind of derivations to the BTech level students, sir?
Yeah, that is what we do here.
Okay. Well, that depends on the syllabus, of course. Yes, sir. Okay, sir. Thank you, sir.
Thank you. 1 2 to 1. One two to one.
Sir, good evening.
Good evening.
Good evening, sir.
Yeah.
The questions, the other topics we are taking the horizontal components as cos theta, but in the fluid mechanics it's a sin theta. Why, sir?
Can you repeat the question? What is
in other topics we are taking the horizontal component as cos theta, but in fluid mechanics it is a sin theta. Why, sir?
Horizontal component is cos theta.
No, it depends on what is your angle here. This is
we
a
are taking the horizontal component as cos theta, but in fluid mechanics it is sin theta. Why, sir?
no, in fluid mechanics why should it be sin theta? See, it depends on what is the notation. If you take angle from the horizontal or if you take angle from the vertical, it will be different. It is a matter of notation. So, you have to see whether it is what the theta means.
Say 1267.
1267. Good afternoon. I am not able to hear you.
Am I audible, sir?
Yeah.
The question is related to the rotating fluid, sir.
Mm-hmm.
In this case, we are using only liquid of particular density. What if we are using liquid of two density, sir? Both of them are immiscible. Then how does the behavior would be? Whether we need to consider individually or whether we need to consider it separately.
Could you repeat it? You have two liquids.
Yes, two liquids, sir. Because in this case we are considering only one liquid of one density. We are having two of different density. For instance, we are having oil and water.
Right.
If we are rotating, how does that behavior?
No, you can. This is a typical question in a exam. You can find the interface between the two liquids. See, it depends on the data. See, whenever you have a rotating system, I did not give you a complete picture. If you increase the rate of rotation, then the liquid can spill out. Okay, the free surface can touch the bottom, free surface can go and hit the top. All kinds of cases are there. So, you can do a similar analysis. You find the pressure distribution in each fluid separately, because in each fluid you have a constant density. So, you will have one constant C1 in one fluid and you have another constant C1, C2 in the second fluid. Now, you look at the interface between the top liquid, which should be of a lighter density, otherwise it will be unstable. There P is P atmosphere, as we have done. Now, for the interface between, say, the other two liquids, if you neglect surface tension effects, the pressure will be continuous. So, you equate the pressure from the equation obtained for the pressure distribution in the bottom liquid with the pressure obtained using the equation of pressure for the top liquid, and you will get a link between the two constants. It is a matter of working it out, but roughly both will be parabolic in nature.
Okay, sir, one more question, sir.
Yeah. I am sorry, I am not able to hear you.
Hello, good evening, sir.
Good evening.
Am I audible?
Yeah.
Can you explain about the shear stress? Because in your morning session, we know only the stress vector and all, but I would like to know about shear stress. What are the changes will happen when the viscosity will react with the shear stress medium?
Okay. Then I have to write down the equations. See, if you have a Newtonian fluid, your sigma xx will be minus p, this is the hydrostatic part, plus twice mu, where mu is the dynamic viscosity, into the strain rate, normal strain rate in the x direction. So, it will be del of Vx del x for an incompressible fluid, and tau xy will be mu into the shear strain rate in the xy plane. So, that will be del of Vy del x plus del of Vx del y. So, this is a Stokes law of viscosity. And this is for Newtonian fluids. Huh? Is it okay? Have you heard it? Okay. Yeah. 1177.
Hello. Good evening, sir.
Good evening.
Is it audible, sir?
Yeah.
Sir, I have two questions, sir. First, I want to know what is the hydrostatic equilibrium. At what condition when that fluid reaches the hydrostatic equilibrium? And one more question, how the fluid statistics applications correlated with the present date? I want to know the applications of that fluid statistics.
You mean fluid statics? Okay. Hydrostatic equilibrium means a state where the fluid is at rest. Although we use the term hydro, strictly speaking hydro means water, but the term is used by many authors for any fluid. For air people use the term aerostatic, but people also use the term hydrostatic. So, hydrostatic equilibrium means a condition where the fluid is at rest. Now, we also have looked at a generalization of that where a container is moving and the fluid is at rest relative to the container. So, that will happen when the relative velocity at the boundaries is 0 and you are going to have curl of rho g 0, that necessary condition which I have derived. If that is not satisfied, then the fluid will not be in hydrostatic equilibrium. Now, applications of fluid statics are in finding forces on bodies, submerged bodies. So, we have discussed some of those and we will be solving some problems. You can have a dam. You have to design a dam which can which will not break or whatever it is. Gates for controlling water in such systems, reservoirs.
Okay, sir. And on my one more question, sir.
Hello, good evening, sir.
Good evening.
Srinivas Kumar from Chennai. The overall program is going very good, nice. But one of our observations is that we can add some more practical examples, case studies, with some applications in this program.
Yeah, you look at the tutorial problems. Tutorial problems have applications. If you want to measure pressure, that is required in many applications, you may do that using manometers or pressure differences. This is the first chapter, so we will have more applications as we go along.
Say 1312.
1312.
Hello.
Yeah.
Sir, I am calling from DMX College of Engineering, Chennai.
Hello.
Yes, please.
Sir, what is the reason for hello?
Yeah.
Sir, can you hear me?
Yeah.
Hello.
Yeah, I can't.
Hello.
Yeah, what is the question?
Sir, the reason for the rise of the water level in the manometer is due to increase in pressure.
Uh-huh.
And what is the reason for fall of the fluid level in the capillary?
No,
What's
which
my question, sir?
No, are you talking about the same application?
Hello?
Or you're talking about two different situations?
No, I didn't get you, sir.
Are you talking about the manometers which I have discussed or something else?
Yeah.
So that change in level is due to change in pressure. We have not looked at capillary effects there.
Is there any other reason for the drop of the fluid level?
Drop of fluid level in which see, in one case, if you due to contact angle, if you dip a capillary in, it might, instead of rising, might go down. Are you talking about that?
Yeah, thank you, sir. Thank you.
1098. তো এই কোশ্চেন গুলো অন্য সেন্টার Yes, please.
Sir, in today's session, we have learned in vectorial form almost all the derivations we have seen in vectorial form. What is its significance in learning it in vectorial form, or represent every pressure field in vectorial form?
No, pressure is not a vector, it is a scalar. See, the form which we have used is a compact form, which so using that we derived the expression for the force on an inclined surface in about 2 or 3 lines. Now that form is valid for any coordinate system. So in many applications, for example, for the inclined surface, I did not take z to be vertically upwards. The z was perpendicular to the surface of the that plane surface, and the plane surface was described by z equal to 0. So that is convenient. So once we have the pressure distribution, to put z equal to 0, and then when you integrate it, you integrate it with respect to y, dy dz, that is your area integral. So for that coordinate system, what should be the pressure distribution? So that is a coordinate invariant form, that P equal to rho g dot r plus c for any fluid with constant density which is at rest.
Thank you, sir.
1176.
Hello?
Yeah.
Hello?
Yes, please.
Hello, can you hear me, sir?
Yeah.
So force of attraction, whether it is more in solids or liquids, fluids, sir.
See, due to shortage of time,
Force of attraction.
See, due to shortage of time, I would prefer questions on today's lecture.
Sir, force of attraction, whether it is more in solids or fluids.
Force of attraction between what?
Solids or fluids?
No, the question doesn't
Molecular.
Yeah, what is the relevance of your question? See, we are short of time and we have to answer a number of questions. What is the relevance of your question to the course which we are doing today, or this 10 days? 1044. I can't hear you. One 1044 ওদের কিছু কোন মান আছে
এতে বল কিছু করার নেই
কাটি দিচ্ছি
1328
Hello.
Yeah.
Hello. Yes, sir. My question is, I am speaking Rashma from IT Bhatta Engineering College. My question is, we have discussed various forces on a submerged body. So, if we increase the temperature of the fluid, is there any change in the forces?
Well, right now we are discussing hydrostatics or fluid statics. So, if your density changes with temperature, then it might change, but that is a minor effect.
In case of minor effect, okay, thank you.
1305.
Good afternoon, sir.
Yeah, good afternoon.
My question is related to rotating fluid. In this case, we have derived the relation or the equation, basic equation for the rotating fluid. We have considered the force rotation of the fluid, but I wanted to know about the rotation of the fluid in the natural condition. Then what will be the equation? How can we recognize the changes in this equation in the case of natural rotation of the fluid?
Okay, suppose the fluid is at rest and the container is at rest, and then you suddenly start to spin it. There will be a what we call a spin up from rest. So, there will be secondary flows. So, there will be a flow in the RZ plane also. Some vortices will be there and then they will decay, and then eventually equilibrium state will be reached where there is only one component of velocity, which is a swirl component V theta. In the transient period you may have a VR and VZ component also. Okay, now let us start the tutorial session, and then if you have time we will come back to questions again.
Good evening everyone. We will be starting with the tutorial on fluid statics. We will be discussing 5 representative problems in this tutorial, which were taught by Professor Sandeepan Ghosh Maulik. We will be discussing about the strategies to solve these problems, and all the problems will be left for you as an homework. So, the first question is, we have to find the difference between the pressures between points A and point B. The tubes connecting the bulbs point A and B contain water and mercury respectively. So, if we have a look at the figure here, the first bulb contains water and the second bulb contains air. This section contains water, this section contains mercury. So, the concept is that the points A and B have to be at the same pressure to be at static equilibrium. So, the pressure at point A is due to the pressure in the bulb plus the pressure of the water column plus the pressure of the mercury column. The pressure at point B is due to the pressure at the bulb B plus the mercury column which is inclined plus the mercury column in this section. So, if you equate these two, you will be able to find out the difference between the two bulbs. Okay, the second question. second question pertains to the measurement of small pressure differences using a micromanometer. So, the micromanometer has two limbs A and B, which are acted upon by differential pressure P1 minus P2. So, the liquid in the chamber A gets depressed by an amount, consequently the liquid in the chamber B gets elevated by the same amount. So, again the concept is we have to identify a horizontal location where we will be able to equate the pressures. So, suppose you identify this location. So, this is 1 and this is 2. So, the pressure at point 1 is due to the pressure here, which is P1, plus the pressure due to this column of water or liquid 1, which has a density rho 1. The pressure at point 2 is due to this elevated section, this combined section, and this liquid of density rho 2. So, if you equate these pressures, you will be able to find out P1 minus P2. Now, one important point to be noted here is, if the liquid gets depressed by a distance delta in the bigger chamber, the equal volume constraint will lead to a rise of height, say h, in the smaller column. So, delta into capital A is equal to h into small a, where capital A is the area of cross section of the bigger chamber and small a is the area of the small tube. You should derive the difference in pressure by assuming that small a by capital is much less than 1, which means the diameter of the tube is much smaller than the diameter of the chamber. So, the answer is P1 minus P2 is approximately equal to G H into rho 2 minus rho 1. The third question is related to the hydrostatic forces acting on gate. So, there is a gate which is exposed to air on one side and it is exposed to water on the other side. Now, the gate is inclined at an angle 30 degrees with respect to the horizontal, and it is the hinge is submerged 1 meter below the water level. So, the hinge is submerged 1 meter below the water level. So, the red area shows the gate and we apply a force F to keep this gate closed. So, the objective is to find out what the force is. Now, pressure will act normally on the surface of the gate as shown. The increasing length of the lines indicate that the force increases with the depth because the pressure will increase with the depth. So, what you need to do is a moment balance about the point H. So, the moment about point H will have two contributions. The first is due to the pressure forces, and the second contribution will be from the force F. So, you have to find out how much force acts on a differential element. Based on that, if you do a moment balance, you will be able to find out the magnitude of the force F. The next two questions will be taken up by my colleague.
Okay, so we move on to the next question, which is question number 4. So this is a question where the variation in density comes into picture. So here we can see that pressure has been given as a function of density in this equation. The pressure has been given as a function of density, and we need to find the pressure as the function of altitude. So I will draw a picture here. So let us say that this is our ground, and I will have my z axis pointing upwards, directly upwards, and gravity is acting downwards. This is gravity. So g is minus g k. So k is a unit vector along the z axis. Now as we all know that the equation for pressure in this particular case of fluid statics is nothing but grad P is equal to rho g. Since there are no body forces along x or y direction, we will for completeness we will denote x horizontally. I will mark it by red. This is x direction, and the y axis will be taken into the page or up from the page, whatever is the right choice of direction. Anyway, the equation for pressure is this: grad P equal to rho g, which finally comes down to dP dz is minus rho g. Now the minus sign here indicates that pressure decreases as we move upwards, which is very intuitive, which we expect as in the to happen in the atmosphere. Now we here have to apply the ideal gas relation, that is PV equal to RT. This has been written for unit mass. Now V can be expressed, so V is the volume of air of unit mass. So V can be basically expressed as 1 by rho, which gives us P equal to rho RT. Now if we use this relation along with this relation here, we will be able to integrate this equation, and we'll have to apply the condition that at z equal to 0, that is at the ground, T is say any T naught, and P, the pressure, is P naught. These two variables we will assume to be constants or known. So if we do that, we can find the pressure as a function of the height in the atmosphere. Actually this problem has already been solved in the previous workshop, so all of you will be able to find the solution and the final answer if you contact your local coordinator. So this is just the procedure to do the problem. We move on to the next problem. This exact same the theory for this exact same problem has already been covered by Professor Ghosmolik. So we will only I will only mention the procedure of solution very briefly here. So as you can see, I will read the problem out first. A 16 centimeter diameter open cylinder, 27 centimeter high, is full of water. Compute the rigid body rotation rate about its central axis, for which 1/3 of the water will spill out and for which the bottom will be barely exposed. So let us assume that, so first let us draw a picture to make the situation clear. So this is a container, it's a cylindrical container. Diameter of the container is given. The diameter is given as 16 centimeter, and the height of the container is also known, which is 27 centimeters. So this is 16 centimeter and this is 27 centimeter, and this is the central axis of the container. Now the cylinder is rotating around the central axis at a speed say omega. So if that happens, then the as mentioned in the problem, initially the cylinder is filled with water up to this level, and as the cylinder starts rotating, the water level at the middle of the cylinder falls, and here it remains the same. So the shape of the water will be the shape of the water surface, free surface, will be something like this, as already explained by sir. So from here we can naturally work out that some of the water will have to spill out of the cylinder, otherwise the free surface of the water cannot have this shape. So this much of water has spilled out of the cylinder. We have to find out the omega, this speed omega, such that this volume of this displaced or spilled out water is 1/3 of the whole cylinder. That's the first part of the problem. So this is again a very simple problem, and the theory of this problem has been worked out in great detail by Professor Ghosh Maulik. So I'll just mention the how to calculate the pressure. So again the pressure will be dp del p del x, del p del x is rho omega square r. I'll make it x. So rho omega square x del p del y. Okay, let me first give the axis. So this will call it as the z axis, where I'm following the same notation as followed by sir previously, and this we will call the x axis, and the y axis will be perpendicularly downwards, so it's pointing this way. So this will be rho omega square y. This is the centrifugal acceleration that is caused by the rotation of the cylinder. This has been mentioned already in today's class, so I am not repeating it. And del p del z will of course be minus rho g. So we have to integrate these three equations to find out the pressure, and then to determine the equation of this surface, this is the free surface, we will use the condition that at free surface P is equal to P atmosphere. So since this surface is left open to atmosphere, the pressure here will be same as the atmospheric pressure, the pressure of the air that is present here, and that is the boundary condition. So we will get the height of this height, if we call say h, this height. So we will get this height as a function of x and y. We'll get this height as a function of x and y if we apply this boundary condition that at the free surface pressure is equal to the atmospheric pressure. Of course this height will also be a function of g, rho and p atmospheric. So if we do that, we'll find the height of this surface, height is a function of x and y. Then we can calculate the volume of the liquid, this whole liquid column. So I'll hash this liquid column. So this blue liquid column, we can integrate and find the volume of this blue hatched part of the liquid column to find out the volume that is left inside the cylinder. It is very simple. So it will be simply integral h dx dy, double integral. So that's the volume of the liquid that is left inside the cylinder. That is, as mentioned in the problem, 2/3 of the initial volume. So initial volume is say I'll call it V0, the initial volume. So V0 is nothing but pi r square h. R is the radius of the cylinder, which is 8 centimeter. Diameter is 16 centimeter, so radius is 8 centimeter. So so this volume is equal to equal to 2/3 of the initial volume. So if we equate these two, we now know h as a function of omega and p atmosphere and rho and all these variables. So if we solve this equation, we will be able to solve for the speed omega. As for the second part, which asks for which angular velocity the bottom I am sorry, the angular velocity is missing from here, so please note that there will be an angular velocity. For which angular velocity, so for which angular velocity the bottom part will be barely exposed. This is again very simple. We'll have to, all we have to do is that at the for the bottom part to be exposed, that means that the liquid shape will be something like this. So I am drawing it by the with a red line, so it will be something like this. So here you can see that the liquid surface, the free surface, has touched the bottom part of the bottom part of the cylinder. So it is touching the cylinder's bottom part at the center of the cylinder, center of this axis. So we have to find the velocity omega square at which this happens. So it's very simple to find out actually. What we will need to do is we need to solve only this equation, that we need to apply this condition that at x equal to y equal to 0, this position is x equal to y equal to 0, h, the height, this is the height, h should be equal to 0. This is our equation. At x equal to y equal to 0, h should be equal to 0, and if we solve this equation, we know h as a function of, we already know h as a function of rho omega and g and p atmosphere, and here rho, g and p atmosphere are known quantities. So if we solve this equation, then we will be able to find the only unknown in this whole equation, that is omega square or omega. So in that way we will be able to find out omega for both the parts. Thank you. Now sir will address some of your queries.
RC 1220. If you have any questions, you can ask. Yeah.
Hello?
Yes, please. Good afternoon.
My question is, how is the determination of magnitude and the line of action of the resultant force? Is of practical interest in this figure?
Okay, I gave you one problem here. You solve one. We had one problem involving force on a gate. So for example, here if you want to know how much of you want to keep the gate closed, so you want to apply a force here, so you need to know the moment if you want to solve this problem. So there you need to know, if you know the resultant force and its point of application, then this problem can be solved very easily. So this is an example of an application where that is required.
Again, my question regarding the plate. How a plate remains in equilibrium under hydrostatic force in water?
You have to have an external force applied to keep it in equilibrium, otherwise it will open. See, you have to apply a force here. Hello? So this is a force. If this force is not there, the gate will open. So to keep the gate closed, you have to apply an external force. So if the force that you have to apply, there is a hinge here, so you have to draw a free body diagram of this gate, and then you will see that the moment of the external force is this F into the distance where it is applied from the hinge and that will be equal to the resultant force into the distance of the center of pressure from this hinge. So, if you know the location of the center of pressure and the resultant force, then it becomes easy for you to find what is the external force required to keep the gate in place. Yeah.
Sir, inclined manometer.
Mm-hmm.
Sir, in inclined manometer, the rise of fluid in manometer tube was measured. That L is measured. Why the delta cannot be measured? The fall of the fluid container.
No, what you typically do is you keep a scale along the inclined tube in the lab. To measure such a small difference delta, how will you do it? That is not easy.
So we have to calculate the delta.
Yes, you will have to calculate the delta. Typically that will be very small.
Okay, sir.
Hello.
Yeah.
Sir, in calculating the center of pressure, we are using the relation h bar equal to x bar plus Ig divided by ax bar, sir. But the x bar is taken from the free surface to the center of gravity of the body, but we are locating the h bar below the center of gravity. Sir, how it is possible?
See, I do not understand your notation. I did not use this notation which you are talking about. See, in my derivation I had kept the origin at the centroid of the immersed plane, inclined plane, and we found that the center of pressure is below. I gave you a physical expression below, yes, below the centroid of the plane. The reason being that the pressure is increasing with depth.
Hello.
Yeah.
Good afternoon, sir.
Good afternoon.
Myself, Professor R. Sharma from Dronacharya College of Engineering, Gurgaon.
Yes, please.
Sir, my question is, you have discussed the two cases, the linearly shaped and the rotation fluid separately.
Yeah.
But in most of the practical problems, we observe that the linear acceleration is accompanied by the rotation also. So in these practical situations, how you will deal how the fluid mechanics, the fluid dynamics deal with such type of problems? This is question number one. The second question is, you have given the concept of ocean current and formation of tides. So I am very much curious because this is a research topic and I want to know, is there any measurement, is any very theoretical concept of this topic so that one can start the research work in this field? Because the ocean current, the imbalance of the force at the two different points, a different line of action create rotational motion, that is all right. But any measurement in this direction or intensity of the tides or intensity of the current has been measured in India or the worldwide? I am very much curious to know this.
Okay, to answer your first question, see, we are looking at a case where you have relative hydrostatic equilibrium. So when I looked at the rotation case, I considered a cylindrical tank. Now in many cases you may not have a hydrostatic equilibrium, so then it becomes a problem of fluid dynamics when you have translation as well as rotation. Rotation means it can be about different axes. We considered a cylinder and the rotation was about the axis of the cylinder, axis of symmetry of the cylinder. So those are the simple cases where you can find the solve it analytically. Otherwise, you may have to solve it numerically. You may have to solve the Navier-Stokes equations in general. Now, I just gave you. Yes.
Is there any mathematics exists that acceleration accompanied by the rotation in aspect?
No, then you have to say what is the shape of the container and what is the axis of rotation. Otherwise, the problem the definition is not complete. See, if you have for the cylindrical tank, we found the pressure distribution to be independent of the angle theta. Now, if you take the cylindrical tank and give it a horizontal acceleration, then it will not be an what should I say, rotationally symmetric case. It may not be rigid body rotation.
What about the second question?
Okay, I had just given you a necessary condition for hydrostatic equilibrium and said that if that is not satisfied, fluid will be set in motion. Now, what happens when the fluid is in motion? That is a problem not of fluid statics or fluid dynamics, and in practice the flow will become turbulent. There are a lot of research has been done and it is of great practical value, as you can understand. So, you have to do a thorough literature search if you want to do research in that area.
Sir?
Yeah.
Good evening, sir.
Yeah, good evening.
My question related to hydrostatic pressure. Am I audible, sir?
Yes.
Yes. There is one formula, as you told, pressure intensity is equal to multiplication of rho GH. This equation will lead to whether it is absolute pressure or gauge pressure.
See, if you say rho GH, then you have to say what is H, otherwise we cannot follow what you are saying. What is H?
Hello?
Yes.
Sir, I want to measure the absolute pressure at a point. Absolute pressure at a point by using instruments. This, if I use this formula rho GH, I think that leads to gauge pressure.
See, you don't use that formula for measuring pressure. What is the device you are going to use to measure pressure, first of all?
That's why I have a doubt. So in my practical experiment, I want to find out the absolute pressure where the ambient pressure is varying. It's not atmospheric pressure. In that case, I am getting trouble.
No, you show us.
How to measure?
You show a schematic.
How to measure?
You show a schematic of your setup, then I can answer your question. What is the instrument you are using to measure the pressure?
Gauge pressure, we are using pressure gauges, sir.
What kind of pressure gauges? What is the fluid? Is it a gas?
It is water only. You know, it is water, sir.
Then,
water.
Then what kind of gauge you are using?
Borden pressure that you are using, sir.
How will you measure pressure of water using a Borden gauge?
Okay, thank you, sir.
Okay. Yeah. 1136.
Can you hear me, sir?
Yeah. Yes.
Sir, actually, I have a doubt. Capillary, sir. Can we apply the capillary concept to jet engines, sir? For gas.
No.
Can we apply the capillary concept to gas, sir?
No.
Hello? Sir, can you hear me?
Yeah.
Sir, actually, can we apply the capillary rise concept to the gas?
No.
Why, sir?
Capillary reaction means what? You explain.
Sir, actually, I have designed a microjet engine, sir. Its size is at level of nano level. So that intake is designed with capillary pipe. So can I run that for the gas?
No, for capillary reaction you need an interface, right? Where is the interface?
Yes, sir. Can we apply the inlet diffuser of the jet engine with the capillary pipe? Can we get the capillary action of gas?
Do you understand the meaning of capillary action?
Yes, sir.
What is
I know
what?
that, sir. Actually, capillary is possible for liquids mostly, sir.
Ah.
So that what I'm just trying with gas.
So where is your interface? You must have an interface, right?
Sir, my interface is just inner combustion product and the outside atmosphere gas.
No, it cannot be done.
So I can't get you, sir.
It cannot be done. There is no capillary action over there.
Sir, main
1133.
Hello.
Yeah.
Good evening, sir.
Good evening.
My question is, my question is on force on plane submerged surface which is inclined. Okay, sir. In this case, you have given that P equals to minus rho g vector dot r vector. So there is a negative sign, and the component of zz and zy all have negative. So how that pressure, total pressure on the surface is coming negative? It should come positive. So means according to the derivation it is coming, the total surface of the pressure is minus rho g sin theta into y, but I think it should come positive. That is the only doubt. Can you please put some light on it?
There is a constant c. That constant c is large.
Okay.
So total thing will be positive. That minus sign.
Total thing will come positive.
See, actually y is upwards. So if you go upwards, the pressure will decrease.
Okay.
That is why you have the minus sign. The
Okay.
Good afternoon, sir.
Yeah, good afternoon.
Sir, sir. Inside the tapered bubble column, sir, is non-Newtonian fluid present, sir, at the particular height, and air is flowing at certain velocity from bottom to top. Sir, what will be the pressure distribution inside the bubble column, sir?
See, today I have just covered fluid statics. What you are talking about is a problem on fluid dynamics.
Inside the tapered bubble column, fluid is just fixed, static inside the tapered bubble column.
If the fluid is at rest, then why are you? What is the significance of the term non-Newtonian? It doesn't matter. The Newtonian and non-Newtonian behavior, we talk about those things when the fluid is flowing. When the fluid is at rest, the stress distribution does not depend on the non-Newtonian or Newtonian behavior. So it is the same.
But, sir, air is flowing.
If the air is
flowing through the
if the air is flowing, then it is not a problem of fluid statics. That's what I told you right in the beginning. Then you have to solve a fluid dynamic problem.
Thank you, sir.
Hello.
Yeah.
Hello.
Yes, please.
Hello. Good evening, sir.
Good evening.
My question is,
My question is about the pressure distribution in fluid, which we have derived inside a linearly accelerated tank. We have derived it in the two coordinate systems. One is a Cartesian coordinate system as well as in cylindrical polar coordinates.
No, that I did for only for the rotation case, not the linearly accelerating. Linear accelerating I did only in Cartesian.
Okay. And at the end, sir, you have derived one shortcut method to get the same equation.
Right.
So my question is it applicable in general, or if no, then what are the circumstances in which we can apply that?
No, shortcut method may not apply in general. That is why it is not discussed in many books. This
under what circumstances we can apply the same?
See, the circumstances is that your coefficient of dx is a function only of x, coefficient of dy is a function only of y, and coefficient of z is a function only of z. So you can write it as a total differential. Sometimes it may not be possible, and you are able to see it by inspection. Sometimes it may be more complicated. Okay.
D of
1307. No. 1273.
Hello, good evening, sir.
Good evening.
Sir, I want to know, will there be any difference between thermodynamic pressure and hydrostatic pressure?
Okay, if it's a compressible fluid which is flowing, there is a difference. If you have a incompressible flow, then the two will be the same, even if the fluid is deforming. For compressible flow, if you accept that Stokes hypothesis is valid, then the two will be the same. So when you study solution viscous flows, Stokes hypothesis may be covered.
Sir, one more question, sir.
Yes.
In the morning, while we are deriving the equations, we have written acceleration A equal to capital dV by dt.
Yeah, I just mentioned it to show where fluid statics stands in general. I didn't derive it, I just mentioned it. So that dV dt will be covered in the kinematics chapter.
Okay, sir. Thank you, sir.
एक बार आपने बोला था ये असाइनमेंट बोलो स्कोर है कोऑर्डिनेटर का दिया.
Alright, now please work out the assignments and submit it to the coordinators of your respective centers. And as you may be aware, we will have a quiz or test, whatever it is you call it, towards the end of this workshop. So if you work out the problems, it will help you in the quiz.